last class we talked about V by F control of induction motor with the steady state equivalent circuit. In that steady state equivalent circuit, what we found, the rate of change of voltage due to the flux that LdI by dt is, or due to the rate of change of current, we found it's only the frequency only we have taken into consideration. But many applications amplitude as well as frequency will change. So, in that case, how the interaction between the fluxes, what is the output power, what is the equivalent model under dynamic conditions, we have to study, and then a control under all dynamic conditions for induction motor, how it works need to be studied now. So, this we call high dynamic performance of induction motor drive. High dynamic performance. Of an induction motor I will write as IM drive. Okay. What is meant by high dynamic performance? A performance similar to a performance similar to a separately excited, this we have studied before, separately excited DC motor. Okay. For a DC motor, we will control the voltage. Okay. You have the armature resistance and then back EMF from the motor. Okay. But the field we will control separately. Okay. Field is kept constant. So, if you see the torque is proportional to phi into I. I is the armature current. So, phi is constant. Then T is proportional to I. How we can get a performance similar to this one, induction motor? So, induction motor we have to find out the I for the induction motor. We have to find the I which is proportional to torque. Also, in DC machine, because of the construction, this flux and I are orthogonal to each other, armature. So, here also we have to find out the flux phi, which is, so this flux phi also generated by a current I. So, for the induction motor, the current which is coming from the starter is a vector sum of the flux producing component and the torque producing component. Now, we have to find out the flux to be kept constant. In vector diagram, this flux which is orthogonal to the torque producing component, torque producing current component. This is, as I told before, the current in the separately excited machine, the flux and the torque producing components are separately adjusted, but in the induction machine it has to be a vector sum. Vector sum means the IS, it should be a vector sum of two currents in this direction, orthogonal. Then only, suppose this is the torque producing proportional to torque, if this should be proportional to phi, then only changing the torque producing component will not affect the flux, because orthogonal. then only we can say the flux is kept constant. So, we have to find out the induction machine from the induction machine model, which is the flux which is orthogonal to the torque producing component. So, let us study the dynamic equivalent circuit model. So, before that briefly we will go to the steady state model. In steady state model, see, let us take the current. This is our IM. This IM plus IR is equal to our IS based on our equivalent circuit model. Here everything is based on the air gap flux. This is IM. This is our IR. This is our IS. Now we know the air gap flux is proportional to IM. So, let the air gap flux is somewhere here. This is equal to LM into IM. Phi m is equal to LM IM. Okay. Now, from this equivalent circuit, the starter flux is equal to, that is starter flux, that is this one. It is coupled here by these two inductance. The phi s is equal to LM IM plus LS into IS. So, IS is proportional to this one. So, along this direction somewhere, this, let us say this is equal to LS IS, our phi s is here. Now, IR is going in this direction. So, if you say the notation, current entering is positive here, current leaving is negative, the phi r, rotor flux is equal to LM IM minus IR LR. LR is the leakage inductance, this one. So, that means how it will be. So, phi m is equal to, so minus IR. So, this is LS IR. So, this actual our IR is this one. So, this direction is minus IR. So, it will be like this, parallel to the IR. LM IM minus LR IR. So, our psi r will be here. See, if you see here from the equivalent circuit, psi r is the one which couples the rotor. That is flux here is coupling this inductance. This is the psi r. After the psi r, you have only seeing the resistance. So, voltage across the resistance RR by S. RR by S is equal to D psi r by dt. Okay. D psi r by dt, assuming flux is kept constant, sinusoidal. So, d psi r by dt is equal to, psi r is equal to sin omega t, it will be j omega psi r into cos omega t. So, this voltage is proportional to psi r, and the voltage and current through RRs is in proportional. So, this psi r and this one will be 90 degree. So, if you look at the IS, previously we have, with respect to air gap flux, we have defined IS as a vector sum of IM plus IR. Also, we can define with another component, which is, let us say, magnetizing component, rotor flux producing component IMR, that is this one, and the perpendicular component, this is also 90 degree. Okay. So, IS originally defined with IM plus IR, vector sum of IMR, can also be defined with a current IMR, which is responsible for psi r, because all these flux are produced by the components of IS, where the air gap flux or the air gap plus the stator leakage, that is the psi s or psi r. So, flux is proportional to the current. So, a current component which is proportional to the flux is already available in IS. So, if you take the flux psi r and the current component which is responsible for psi r, that is we are taking as IMR. IMR is proportional to psi r. Then there is an orthogonal component that is perpendicular to IMR, which is the torque producing component. So, this IMR plus IR is equal to IS. So, if we find an equivalent circuit based on this one, then that is the equivalent circuit that is required for high dynamic performance drive application. That means we have to keep this IR which is proportional to IMR, which is perpendicular to IR. We have to keep varying during the torque production, and this IMR we have to keep constant, so that psi r is also constant. So, there is a decoupled control possible in the same way as in separately excited DC motor. But if you see here, this is based on steady state equivalent circuit. Under dynamic conditions, this magnitude of IS can vary. So, this psi r with respect to psi m, position with respect to IS can vary. So, what we want to find out, to resolve the current, to resolve the current IS along phi r and perpendicular to it, to phi r, we need to know the position of psi r under all dynamic conditions. So, this is the problem here. So, we need an equivalent circuit which is valid under all dynamic conditions. That means, whenever the IS varies or the flux amplitude varies, psi m amplitude varies, psi s varies, how the relative position of all these vectors. From that, find out the psi r and resolve psi r. So, resolve IS along psi r and perpendicular to it, and keep the component along psi r constant, the current component. So, psi r will be kept constant. So, same like separately excited machine, the flux is kept constant, and we are controlling the orthogonal component for the torque variation. So, let us study the dynamic equivalent circuit for the induction machine. Let us go to that one. From there, we will derive the resolve the current IS along psi r and perpendicular to IR. This is called the field oriented control, the famous or vector control. For the dynamic equivalent circuit, here we will use the space vector notation. So, we studied space vector in the context of space vector PWM. So, again we will just remember some of the basics here. So, when the machine is excited with a 3 sinusoidal currents, when the machine is excited with 3 sinusoidal currents, let us say this is RYB or ABC. We know that there will be a flux, air gap flux, which is tracing a circle, and the speed is omega s, the synchronous frequency of this one. And this flux space phasor is, we have put as Ns into Is, is the MMF. This is equal to Ns I alpha plus Ns plus J Ns I beta. So, even though this flux, the rotating flux is produced by three phase quantities, we can also have an equivalent two phase quantity alpha beta. So, this is the flux which is already there in the air gap. Now, this flux is proportional to current. If you remove this ns, this is a constant, then we can have a definition for current space phasor. This is also equal to n alpha plus j I beta. This is called the current space phasor. Space phasor or vector, anything is okay. Both are same. Mu this current is produced by the three currents IA, IB, IC. This is also this current space phasor. This current is sinusoidal current is flowing into the machine is due to the excitation with the sinusoidal voltages. That voltage and current will have a phase angle of phi. So, we can also have a definition, equivalent voltage space vector definition, V alpha plus JV beta. Okay. So, Vs, what is Vs? Vs is equal to, there is a mod plus there is an angle. This angle will measure with respect to the alpha axis. This is the angle alpha. And this alpha we will always place. Alpha is placed along the A phase axis. Okay. So, this is alpha, this is beta. Now, our ABC quantities are A is along this direction, B is 120 degree, C is also 120 degree. Okay. So, Vs, so if our, let us take our Vs is equal to Vs mod e raised to j omega t, because all these flux space phasors, the flux and current and voltage space vector which rotates, the tip of the vector rotates with angular frequency omega t, that is excitation frequency. But there is only but there is always a fixed phase difference between the voltage and current, okay, during steady state. In dynamic conditions, this angle as well as the magnitude varies. So, this is our Vs. Now, let us write down the phasor quantities for the induction machine. Let us take the induction machine is a squirrel cage induction machine where the there is no voltage excitation from the rotor side. Rotor is short circuited. So, first we draw our alpha axis. This is the beta, this is the alpha axis, and alpha axis is placed along our A phase axis. Okay. This is the alpha and this is the beta, and we are measuring the angle with respect to alpha axis. So, let us take a general position of Vs, voltage space vector. Let us take Vs is equal to e raised to j gamma 1, which is gamma 1. Gamma 1 is this angle. This is a function of time as Vs varies. So, a general position, this Vs e raised to j gamma 1. See, Vs is equal to, Vs is our space vector which is a magnitude, so we will add an angle. So, we will write that way. Vs is equal to Vs, this is the amplitude, into e raised to j, e raised to j gamma 1. This is the one, gamma 1. Now, because of the voltage space vector, assuming it is the machine is excited with sinusoidal current. So, because of this voltage space vector, now this voltage space vector, it has an alpha component and beta component. Also, the projection of this Vs along the ABC axis will give the instantaneous values or the excitation values for the ABC voltages. So, if you know the instantaneous position of Vs and its magnitudes, we can find out the alpha, beta as well as ABC. So, we do not require the 3 phase quantities. Here one quantity is sufficient, that is the voltage space vector, the one quantity in polar form, the magnitude and the angle with respect to alpha axis. Now, when the machine is excited with a voltage space phasor, there will be a current space phasor also, and current space phasor will not be, these two vectors will not be collinear, there will be a phase difference. Let us take the IS. IS is somewhere here. IS, the angle, instantaneous angle is gamma. So, it will be equal to IS magnitude e raised to j gamma. Okay. Now, the rotor is rotating. So, if you see, the rotor ABC axis will have a varying angle with respect to the starter ABC angle, and the angle or the rate of change of angle is proportional to the rotor speed. So, let us say the rotor axis is somewhere here. Rotor A phase axis. Okay, I will write it bold. Rotor A phase axis. So, this is moving with a angle sigma. Sigma is also a function of t. What is d sigma by dt? No, d epsilon by dt. D epsilon by dt is equal to omega r, rotor speed. Okay. So, rotor also has ABC axis. So, suppose if we measure the rotor current with respect to a rotor ABC axis, the angular velocity of the rotor current space vector will be proportional to the slip frequency. So, let us say there is a rotor current IR. IR is equal to, with respect to rotor axis, IR is equal to, let us take this is theta, e raised to j theta, where d theta by dt is equal to omega slip. Okay, but theta is the angle. We are always measuring the angle. Okay, and there is no rotor excitation voltage. Okay, because rotor is short circuited. Now, relative position of the rotor voltage, starter voltage, starter current, and rotor current is known. So, let us write down the rotor and the starter voltage space vector based equation. That is, a starter and rotor equations. This is space phasor based equations. We are not using the ABC component and alpha beta. These are all called space phasor or space vector based equation. Let us start with the rotor applied voltage Vs. When the starter is applied with a space vector Vs, it will have the starter drop. This is the space vector Is plus starter self inductance mutual plus leakage, that we will represent as LSS. This is called self inductance into d by dt of Is. So, the moment d by dt of Is we are taking into consideration, Is has a magnitude as well as angle, both are varying. So, d by dt we are taking into consideration the variation of both, here we will take care. Now, due to rotor current and there is a mutual inductance between starter and the rotor, there is a coupled voltage to the stator due to the rotor current. So, what will be that? So, due to the mutual inductance M into d by dt, if you see here IR is defined with respect to rotor axis, that is IR into e raised to j epsilon. See, originally IR is defined with respect to rotor axis, that is here. Now, all the quantities, now stator means everything we have to represent with the same axis. So, what happens? We have to multiply it by e raised to j sigma. This IR is equal to IR into e raised to j theta. This we are multiplying with e raised to j theta. So, that this is defined with respect to stator. Respect to stator alpha axis. See how this is done. Let us go to the vector notation. This is very easy. Let us take this way. Say there is an alpha beta axis. There is a current IR. This current IR is defined with respect to this axis. This axis means there is a perpendicular axis also for that one. So, we require a perpendicular axis for that also. This is our angle theta. So, that means this IR will have a component along this alpha 1 axis and beta 1 axis. What is IR alpha 1 is equal to IR magnitude is equal to IR into cos theta, and IR beta 1 along beta component is equal to IR cos beta. So, with respect to alpha 1 and beta 1, IR, the current space phasor is equal to IR alpha 1 plus j IR beta 1. This is equal to IR cos theta plus j IR cos theta. Oh, sorry, this is theta. Okay, this is the one. Now, this IR we are defined with respect to alpha beta 1. This can also be defined with alpha beta. Any axis we can define it. Now, if you see here, if this difference between the two axes, suppose this is theta, then what is the component IR alpha now? Let us take the IR alpha is equal to, magnitude is the same, IR into cos of theta plus epsilon. Now, in the new axis, IR beta is equal to, again the magnitude IR into sine, this is sine. Here also IR beta is not cos, it is sine, orthogonal. Okay? That means the IR, we are splitting into one real component and imaginary component. So, this will contain the cosine function, this will contain the sine. So, IR sine here theta plus epsilon. So, this in space vector notation, magnitude is the same. IR is equal to IR into e raised to j theta plus epsilon. Okay. So, when we transfer to this axis, if the movement is in this direction, angle we are measuring in this direction, angle is increased, theta plus epsilon. Now, if you have an axis somewhere here, then that angle has to be subtracted. So, depending on the rotation. So, in the previous case here, originally the IR was defined with respect to rotor axis. Now, we are defining with respect to the stator axis, that is why e raised to j epsilon here. So, that means all the voltage term appearing in the stator, whether due to the stator current or the rotor current, are defined with respect to the common reference axis alpha beta. So, if you transfer this into the real and imaginary component, you will get the alpha beta component. Okay? Or if you transfer this to the ABC component, you will get the equivalent ABC component. So, this one equation is sufficient to get the alpha beta or ABC component. This is for the stator. Now, let us take the rotor equation. So, let the rotor equation be, we will take the rotor equation in a different color. This is the stator. Now, we will take the rotor. Rotor applied voltage is 0 because it is short circuited, but there is a rotor current. So, you have RR into IR. See here, if you want to have an equivalent circuit, steady state equivalent circuit or dynamic equivalent circuit, both the stator and the rotor we have to define with respect to the common reference phase axis. Now, the common reference axis is alpha axis placed along the A phase axis, that is RR IR into e raised to j epsilon. That means this IR underscore means it is a space vector, it has a magnitude and angle defined originally with respect to rotor axis. Now, multiplying by A sigma, the whole thing is defined with respect to the stator A phase axis. IR into e raised to epsilon plus rotor self inductance, mutual plus leakage, LRR into d by dt IR. So, the current which has a frequency of slip frequency, which will produce due to the self inductance, there is a rotor voltage. Okay. Now, this rotor voltage we want to transfer to the stator. So, this is a space vector quantity. This space vector quantity, if you want to transfer to the stator reference axis, we have to multiply it by e raised to j epsilon. So, here this e raised to j epsilon is the voltage term we are transferring to the stator. So, this will not come into the d by dt. So, d by LRR into d by dt IR underscore, this is the voltage appearing in the rotor circuit due to the rotor frequency of self frequency. Now, this voltage term we are transferring to the stator, that is by e raised to j epsilon. Now, let us say the mutual inductance. Due to the current in the stator, there is a coupling, there will be a flux generated, that flux is proportional to that current and the mutual inductance which would be coupling to the rotor. Now, this IS m into d by dt IS. IS is originally defined with respect to the stator. Now, when this current, how much of this current, what way it induce voltage in the rotor means, this current term we have to find the component of the, we have to define this current with respect to the rotor axis. Then multiplied by B, M is the voltage term induced in the rotor due to the stator current. So, IS we have to bring back to the rotor circuit. If you see IS is originally defined with respect to alpha, now we have to define with respect to the rotor. So, we have to go this way. Previously for the rotor it was plus j epsilon. Here we are going this way, angle is reducing. So Is into e raised to minus j epsilon. This is the voltage term appearing at the rotor due to the stator current. Now this voltage term also we have to bring it to the stator side. So outside we have to multiply it by a raised to j sigma. Why? This term is defined with respect to rotor axis. Okay. This term is defined with respect to rotor axis. Now multiplying by e raised to j epsilon, this will bring the rotor voltage also along the stator axis. That means common reference axis. So now we have the stator as well as the rotor voltage terms with respect to a common reference axis. So our now split into your ABC alpha beta axis, component, you will get the dynamic equations for the stator and the rotor. So let us. So here if you see all the voltage and voltage of stator and rotor we defined with respect to a alpha beta axis, where the alpha is placed along the A phase axis. This is called stationary reference frame axis. Stationary reference frame axis. Because alpha is placed along the stator A phase axis, that is stationary. So it is called stationary reference axis, that is the alpha beta. Okay. So this is very simple. I will again go through this equation so that you will be able to understand the transformation from one reference to other reference frame. So if you see here, I will again explain for clarity. See, we want to define the stator voltage and rotor current with respect to a common reference axis. So if you see here, this is the alpha axis, this is the beta axis, and alpha is placed along the A phase axis and beta is perpendicular to that one. Okay. Now when the machine is excited with sinusoidal currents or sinusoidal voltages in the stator, stator will have a ABC current, so it will have an equivalent current space phasor Is. Now let us say the voltage space phasor Vs is defined as Vs underscore voltage space phasor. It has a magnitude and angle. Angle we are referring with respect to the alpha axis, which is placed along the A phase axis. Now this voltage space phasor generate three phase currents. So we have an equivalent current space phasor definition, but this voltage and currents are not collinear. There is a phase difference. But instead of worrying about the phase difference, we are only taking the angle of the space vector with respect to the A phase axis. So Is has an amplitude and e raised to j, this one gamma here. Now because of the relative motion, there is a flux generated and relative motion of the stator and the rotor. Rotor will have a rotor current, and we know that previously we studied the rotor current frequency will be proportional to the slip frequency. So if we assume rotor also assumed to have an equivalent ABC, equivalent is all the rotor current is also generated due to an equivalent ABC phases, same like stator. And if you see the rotor A phase axis is here, but the rotor A phase axis will be moving away from the stator A phase axis because of the rotation. So the instantaneous angle is epsilon. Now with respect to rotor A phase axis, if you stand on the rotor A phase axis, the rotor current space vector will have a magnitude and you will have an angle theta, which will be varying from the rotor A phase axis with a speed equal to omega slip, that is d theta by dt is equal to omega slip. Now if you stand on the rotor, you will see that rotor A phase axis is moving away from the stator with an angle epsilon, that is due to the rotation, and d epsilon by dt is equal to rotor speed. So, the relative position of the voltage and current space vector we have defined. Now, we want to have the equivalent voltage space vector equation. So, the Vs underscore is equal to, when the machine is excited with Vs voltage space vector is equal to, it will have a resistance drop Rs plus Is. Is is the our induction machine total current space vector Is plus LSS plus d by dt of Is. Now, Is is originally defined with respect to alpha axis. So, this resistance drop and the self inductance of the stator are defined, that voltages are defined with respect to the A phase axis. Now, because of a rotor current, there can be a voltage induced at the stator due to the mutual inductance. Why mutual inductance? All the flux due to IR will not couple to the stator. There is a mutual plus leakage part is there. So, due to the mutual only, there is a link between the stator and the rotor. So, if you see here, M into d by dt IR underscore is the one the current defined with respect to the rotor axis. Now, the voltage term, this current originally defined with respect to the rotor axis, we have to bring to the stator axis. That is why angle is increased now. Rotation is in this direction. So, now the new angle is theta plus epsilon. Theta is already inside this one IR underscore. So, this is the current. Now, the rotor current is defined with respect to the stator axis, then the voltage time is equal to M into d by dt of this one. Okay. Now, let us go to the rotor. Applied voltage is equal to 0. But due to the rotor current, that is IR underscore, we will have a voltage equation RR into IR underscore here. This is the voltage term defined with respect to rotor axis. Now, the voltage term, if you want to bring it to the stator, you have to multiply by A raised to J epsilon. Similarly, the voltage induced due to the self inductance in the rotor is equal to LRR d by dt IR, where IR has a magnitude of IR and angle is equal to E raised to J theta, that is slip frequency into the time. Now, this is the voltage. This voltage also we want to bring it to the stator. So, we are multiplying by E raised to J epsilon. Now, there is a current term which is originally defined with respect to the stator axis, that will induce a voltage in the rotor. So, this current originally defined with the stator axis has to be defined with respect to the rotor axis. So, from here it has to go here. So, minus J epsilon, then d by dt m, this is the voltage term induced at the rotor. Now, the whole voltage term we are transferring to the stator by E raised to J epsilon. So, the epsilons outside the bracket will not come into the d by dt, because the voltage term we are transferring to some other axis, that is all. Now, as I told, we are defining the stator voltage and current with respect to a common reference phase axis, that is alpha beta. That alpha is placed along the A phase axis. This is also called stationary reference frame axis. Okay. Now, what we want? We want to find out the instantaneous position of the rotor flux. Okay. So, if you know the instantaneous position of the rotor flux, let us go to the next page. This is your alpha, beta. Suppose we have defined our, we have placed the position, relative position of the voltage and current. Similar way we can position of the relative flux psi r also. Let psi r makes an angle rho. Now, for vector control applications, the IS, as I told, IS we have to define with respect to psi r, that means component along the psi r and perpendicular to psi r we have to find out. So, if we can find out another axis, define a dq axis, okay, sorry, this is d, this is q. This D is along the psi r axis. This is D, this is Q. Now, dq is a general rotating axis. If this rotating speed is equal to omega s, that is d rho by dt is equal to omega s, then this general rotating dq axis is moving with respect to a synchronous speed. So, this is called, then the dynamic equations, if you are generating based on the dq, is called synchronous frame reference. Synchronous frame reference. If this dq is placed along the rotor axis, that means as the rotor varies, this d also placed along the rotor axis, then we can say the dynamic equations developed on this dq is defined with respect to the rotor reference axis. Now, if we know the instantaneous position of the if you know the instantaneous position of the psi r, then we can position dq along psi r. This is called synchronous reference. So, what is the advantage? So, if our original IS is here, then IS can be split along psi r and perpendicular to it. That means there is a current component along this one. This is our original IMR, and this is the current. Perpendicular to that one will be our IR. So, if you know the phi r and place the dq axis along the psi r, that is d is all the time for any dynamic conditions, d is placed along psi r, then the component of IS along d will be proportional to the rotor flux producing component phi r, and any component perpendicular to that one IR will be the torque producing component. So, if we can find out our dynamic equations with respect to dq, a synchronous rotating reference frame with dq placed along psi r, then that dynamic equation condition, that dynamic voltage and current conditions are the one useful for our vector control applications. So, what we want to know now here is, let us find out from the stationary reference frame, let us find out the dynamic equations under a general dq, a general rotating dq reference frame. Okay. From that one, place the dq along the psi r, then get the conditions for the vector control applications, such that the IS can be split along a component along the psi r and perpendicular to it. So, that way we can have a decoupled control, same like in a separately excited machine. This will study in the next class.